Developing the library's functionality with test-driven development. Now that we've extracted the logic into lib and left the argument collecting and error handling in main, it's much easier to write tests for the core functionality of our code. We can call functions directly with various arguments and check return values without having to call our binary from the command line. Feel free to write some tests for the functionality in the config new and run functions on your own. In this section, we'll add the searching logic to the mini-grep program by using the test-driven development process. This software development technique follows these steps. 1. Write a test that fails and run it to make sure it fails for the reason you expect. 2. Write or modify just enough code to make the new test pass. 3. Refactor the code you just added or changed and make sure the test continues to pass. 4. Repeat from step 1. This process is just one of many ways to write software, but TDD can help drive code design as well. Writing the test before you write the code that makes the test pass helps to maintain high test coverage throughout the process. We'll test drive the implementation of the functionality that will actually do the searching for the query in the file contents and produce a list of lines that match the query. We'll add this functionality in a function called search. Writing a failing test. Because we don't need them anymore, let's remove the print line statements from lib and main that we use to check the program's behavior. Then, in lib, we'll add a tests module with a test function, as we did in chapter 11. The test function specifies the behavior we want the search function to have. It will take a query and the text to search for the query in, and will return only the lines from the text which contain the query. Listing 12:15 shows this test, which won't compile yet. This test searches for the string duct. The text we're searching is 3 lines, only one of which contains duct. We assert that the value returned from the search function contains only the line we expect. We aren't able to run this test and watch it fail because the test doesn't even compile. The search function doesn't exist yet, so we'll add just enough code to get the test to compile and run by adding a definition of the search function that always returns an empty vector, as shown in listing 12:16. Then the test should compile and fail because an empty vector doesn't match a vector containing the line safe, fast, productive. Notice that we need an explicit lifetime, A, defined in the signature of search and used with the contents argument and the return value. Recall in chapter 10 that the lifetime parameters specify which argument lifetime is connected to the lifetime of the return value. In this case, we indicate that the returned vector should contain string slices that reference slices of the argument contents rather than the argument query. In other words, we tell Rust that the data returned by the search function will live as long as the data passed into the search function in the contents argument. This is important. The data referenced by a slice needs to be valid for the reference to be valid. If the compiler assumes we're making string slices of query rather than contents, it will do its safety checking incorrectly. If we forget the lifetime annotations and try to compile this function, we'll get this error. Rust can't possibly know which of the two arguments we need, so we need to tell it. Because contents is the argument that contains all of our text, and we want to return the parts of that text that match, we know contents is the argument that should be connected to the return value using the lifetime syntax. Other programming languages don't require you to connect arguments to return values in the signature. Although this might seem strange, it will get easier over time. You might want to compare this example with the Validating References with Lifetimes section in Chapter 10. Now let's run the test. Great! The test fails. Exactly as we expected. Let's get the test to pass. Writing code to pass the test. Currently, our test is failing because we always return an empty vector. To fix that and implement search, our program needs to follow these steps. Iterate through each line of the contents. Check whether the line contains our query string. If it does, add it to the list of values we're returning. If it doesn't, do nothing. Return the list of results that match. Let's work through each step, starting with iterating through lines. Iterating through lines with the lines method. Rust has a helpful method to handle line-by-line iteration of strings, conveniently named lines, that works as shown in listing 1217. Note, this won't compile yet. The lines method returns an iterator. We'll talk about iterators in depth in Chapter 13, but recall that you saw this way of using an iterator in listing 3.5, where we used a for loop with an iterator to run some code on each item in a collection, searching each line for the query. Next, we'll check whether the current line contains our query string. Fortunately, strings have a helpful method named contains that does this for us. Add a call to the contains method in the search function, as shown in listing 1218. Note, this still won't compile yet. Storing matching lines. We also need a way to store the lines that contain our query string. For that, we can make a mutable vector before the for loop and call the push method to store a line in the vector. After the for loop, we return the vector, as shown in listing 12.9. Now the search function should return only the lines that contain query, and our test should pass. Let's run the test. Our test passed, so we know it works. At this point, we could consider opportunities for refactoring the implementation of the search function while keeping the tests passing to maintain the same functionality. The code in the search function isn't too bad, but it doesn't take advantage of some useful features of iterators. We'll return to this example in Chapter 13, where we'll explore iterators in detail and look at how to improve it, using the search function in the run function. Now that the search function is working and tested, we need to call search from our run function. We need to pass the config query value and the contents that run reads from the file to the search function. Then run will print each line returned from search. We're still using a for loop to return each line from search and print it. Now the entire program should work. Let's try it out. First with a word that should return exactly one line from the Emily Dickinson poem, Frog. Cool. Now let's try a word that will match multiple lines, like body. And finally, let's make sure that we don't get any lines when we search for a word that isn't anywhere in the poem, such as monomorphization. Excellent. We've built our own mini version of a classic tool and learned a lot about how to structure applications. We've also learned a bit about file input and output, lifetimes, testing, and command line parsing. To round out this project, we will briefly demonstrate how to work with environment variables and how to print a standard error, both of which are useful when you're writing command line programs. Working with environment variables. We'll improve minigrep by adding an extra feature, an option for case-insensitive searching that the user can turn on via an environment variable. We can make this feature a command line option and require that users enter it each time they wanted it to apply, but instead we'll use an environment variable. Doing this allows our users to set the environment variable once and have all their searches be case-insensitive in that terminal session. Writing a failing test for the case-insensitive search function. We want to add a new search case-insensitive function that we'll call when the environment variable is on. We'll continue to follow the TDD process, so the first step is again to write a failing test. We'll add a new test for the new search case-insensitive function and rename our old test from oneResult to case-sensitive to clarify the differences between the two tests as shown in listing 1220. Note that we've edited the old test's contents too. We've added a new line with the text duct tape, using a capital D that shouldn't match the query duct, when we're searching in a case-sensitive manner. Changing the old test in this way helps ensure that we don't accidentally break the case-sensitive search functionality that we've already implemented. This test should pass now and should continue to pass as we work on the case-insensitive search. The new test for the case-insensitive search uses Rust as its query. In the search case-insensitive function we're about to add, the query Rust should match the line containing Rust with a capital R and match the line trust me, even though both have different casing from the query. This is our failing test, and it will fail to compile because we haven't yet defined the search case-insensitive function. Feel free to add a skeleton implementation that always returns an empty vector, similar to the way we did for the search function in listing 1216 to see the test compile and fail. Implementing the search case-insensitive function. The search case-insensitive function, shown in listing 1221, will be almost the same as the search function. The only difference is that we'll lowercase the query and each line So whatever the case of the input arguments, they'll be the same case when we check whether the line contains the query. First, we lowercase the query string and store it in a shadowed variable with the same name. Calling to lowercase on the query is necessary, so no matter whether the user's query is Rust, Rust with all caps, Rust with one capital, or Rust with strange capitals, we'll treat the query as if it were just Rust lowercase and be insensitive to the case. Note the query is now a string rather than a string slice because calling to lowercase creates new data rather than referencing existing data. Say the query is Rust with a capital U and a capital T as an example. That string slice doesn't contain a lowercase u or t for us to use. So we have to allocate a new string containing Rust in all lowercase. When we pass query as an argument to the contains method now, we need to add an ampersand because the signature of contains is defined to take a string slice. Next, we'll add a call to lowercase on each line before we check whether it contains query to lowercase all characters. Now that we've converted line and query to lowercase, we'll find matches no matter what case of the query is the. Great, they passed. Now let's call the new search CaseInsensitive function from the run function. First, we'll add a configuration option to the config struct to switch between case-sensitive and case-insensitive search. Adding this field will cause compiler errors because we aren't initializing this field anywhere yet. Note that we added the case-sensitive field that holds a Boolean. Next, we need the run function to check the case-sensitive field's value and use that to decide whether to call the search function or the search case-insensitive function, as shown in listing 1222. Note, this still won't compile yet. Calling either search or search case insensitive based on the value in config case sensitive. Finally, we need to check for the environment variable. The functions for working with environment variables are in the env module in the standard library, so we want to bring that module into scope with a use standard env line at the top of lib. Then we'll use the var function from the env module to check for an environment variable named case insensitive as shown in listing 1223. Here we create a new variable, case sensitive. To set its value, we call the environment variable function and pass it the name of the case insensitive environment variable. The environment variable function returns a result that will be the successful OK variant that contains the value of the environment variable if the environment variable is set. It will return the error variant if the environment variable is not set. We're using the isError method on the result to check whether it's an error and therefore unset, which means it should do a case-sensitive search. If the case-insensitive environment variable is set to anything, isError will return false and the program will perform a case-insensitive search. We don't care about the value of the environment variable, just whether it's set or unset. So we're checking isError rather than using unwrap, expect, or any of the other methods we've seen on result. We pass the value in the case-sensitive variable to the config instance so that the run function can read that value and decide whether to call search or search case-insensitive. Let's give it a try. First, we'll run our program without the environment variable set and with the query to, which should match any line that contains the word to in all lowercase. Looks like that still works. Now let's run the program with case-insensitive set to 1, but with the same query to. If you're using PowerShell, you need to set the environment variable and run the program in 2 commands rather than 1. If you're using, they don't say this, but if you're using Linux or Mac, I suppose, you can, I guess, you can use the env utility and just prepend cargo run, prepend that with env, and then I think maybe a space, and then this, or maybe you need the colon, I don't remember, but anyway, you can run it in the same line. We should get lines that contain to that might have uppercase letters. Oh, here it is. Yes. Oh, so you don't even have to use the env utility. You just put in case-insensitive equals 1, cargo run to poem.txt. Excellent. We also got lines containing to with a capital T. Our mini-grep program can now do case-insensitive searching controlled by an environment variable. Now you know how to manage options set using either command line arguments or environment variables. Some programs allow arguments and environment variables for the same configuration. In those cases, the programs decide that one or the other takes precedence. For another exercise on your own, try controlling case insensitivity through either a command line argument or an environment variable. Decide whether the command line argument or the environment variable should take precedence if the program is run with one set to case sensitive and one set to case insensitive. The standard environment module contains many more useful features for dealing with environment variables. Check out its documentation to see what's available.